that down, then what happens is that that parallelogram essentially becomes the area of that region. All right? So somehow the area of this deals with the cross product, right? Something in here, we require a cross product to approximate that area. Let me keep going here. So I say here, we see our strange-shaped region, right, becomes a rectangle in the xy plane. We still need to determine how this area in region D, of region D in the xy plane is related to the rectangle S in the UV plane. So this is the UV plane, this is the XY plane. So this is me basically explaining exactly what I just said about the cross product. You have some vector function, right? It's in three-dimensional space because you have to be able to do a cross product, right? So to do a cross product, you need three-dimensional space, which is why I use a zero component for the Z. And so now I cross it and I get an area that is approximately the area of the parallelogram, which is the magnitude of the cross product. Then we use a property of cross products that we can pull constants out, okay? So we can get this, and then we actually calculate the cross product. See, this is the theory. I'm not getting into the real details of this, all right? We do the cross product of this, of the two partials, and when we do that, dun, 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 at the very end, we get this right here. And that right there is going to be the important part of this. That is the quantity that we have to scale by if we're going to convert from one coordinate system to the other. So we let the number of rectangles go to infinity, and finally after all this we get a formula for dA. Here's our function when we convert it to the new coordinate system, right? So when we convert the x over and the y over, we need to scale, right? We need to scale right here by this. I know that's a terrible explanation, but it's the problem is, again, we could spend like the entire class going through each of these computations. And at the very end, you're going to get this, and then when we go to do it in spherical, everything changes because now our picture is not on a flat sheet of paper anymore, it's on a surface that's in 3D. So I have to go through the whole proof again, but we don't know how to draw surfaces in 3D with vector functions. So we have to loosely go through this, yes?
I think it made sense that the variable added at the end is just scaling it to the right coordinate system.
So you're okay with it? Okay. All right, yes?
It's kind of like how they say maps don't accurately represent Earth, right? Because I mean, when you're going from a sphere to flat, it changes things.
Yes, that's
Greenland's bigger than on the map, and Russia likes that map because it makes it look weird. Right?
That's true. So what you're saying is right, but it's not really connected to this because we're not going from 3D to 2D.
Yeah.
We're not doing that here. Here we're going from 2D to 2D, and we just want to know when we change coordinate systems how much we have to scale to keep everything in line, right? I think what you're referring to, maybe I'm wrong, is that you can't take a map of a sphere and map it onto a flat sheet of paper. You give up something. You either give up distance or you give up angle, one or the other. Usually a map, most maps that we use, like when we're on the road, no one uses a map, but you know what I mean, right? Most physical maps, they say this is a map that preserves distances. Versus if you're on a ship and you're navigating, they use maps that preserve angles because you want to head that way, and yeah, you're going to get there eventually, right? So you just head that way. Sometimes you need a map to know how far to go, and the angle doesn't matter so much. So that's a whole other conversation, but maybe what you meant was that there's no easy way for me to just translate this 2D thing into 3D. There's just no way. It's going to be harder to do. So, all right. The book goes through this as well, so if you feel unsatisfied about this proof, the book goes through it as well. Or if you really want to get into it, just come to my office during my office hours. We'll sit down and we'll grind through this proof, okay? So this is what we get, all right? If we are ever in two-dimensional space, if we're ever in two-dimensional space and we do a change of variables, where our x gets changed into some function of u and v, and our y gets changed into some function of u and v as well. So if we do this change of variables, then we will do our double integral will change from its original domain with respect to x and y. It'll change to the new domain, whatever that is. Our function will have to be switched over. Our x's and y's will have to be switched over. And we will have to scale by this and then integrate with respect to u and then v. So I'm going to write that down right here. F now needs to be switched over. X has to be switched. Y has to be switched. Then you have this thing, which is called the, did I go past that already? I've said it. It's called the Jacobian. I'm going to say it at the end of this. There we go. It's called the Jacobian, it's called the Jacobian or Jacobian determinant, right? You'll hear it different ways. I want to write this on the board because I'm going to need it. Partial x with respect to u, partial y with respect to v, minus partial x with respect to v times partial y with respect to u. And then du dv. There it is. So this is the generic formula that if we ever convert from any coordinate system to any other one, we have to do that computation. Yes?
So for the absolute value of,
Yeah, it's the absolute value.
yeah, so that's the area, but like, I'm assuming that means the value negative. What does that mean if the value's negative?
Say again. Well, this won't, the absolute value won't, we're always going to take the positive scale.
Right, because it's an area.
Yes.
It's just specifically area.
Yeah.
But in the case of like the inside being negative,
Well, remember when you had two vectors and you cross them, right? You get a third vector that's orthogonal to both. And then the magnitude is just the length of that vector. If you cross them the other way, like instead of crossing this one with this one, you cross this one with this one, your vector goes the other direction. So all we care about is its magnitude. Does that make sense?
Yeah.
Okay. All right, I think maybe we should just do an example, right? So let's do the, I think the most natural example right now would be let's prove the r from the polar, right? Remember that r popped out? Let's prove it. Let's prove that we get an r that pops out anytime we convert from Cartesian to polar. So let's let x be equal to r cosine theta. Let's let y be equal to r sine theta, right? That's our polar. But because I want to do everything using that formula, I'm going to scratch this. Guys, can y'all just a little bit, just because I hear it's distracting. U cosine, do you have a question though?
Yeah, so does that work for both the polar, the cylindrical, the spherical, just multiple types?
Okay, so the question is, does this work for the cylindrical, spherical? Yes and no. This was a two-dimensional formula for two-dimensional case. If we do x, y, z, then this is going to change. And I'm going to do it, okay? We're just not, so this is only two-dimensional. And the proof in the book is only for the two-dimensional, which is why I said I don't like doing the proof, because we want to work in three-dimensional. So, all right. Everyone understand? All I did there is replace the r with u and the theta with v, right? Just so it matches up with that formula. Okay, let's actually compute the Jacobian determinant. So I need those partials, right? So let's just write down the partials, then we'll put it in there. Partial x with respect to u first. What's the partial of x with respect to u? Cosine v. You're taking the derivative of this, you're treating u like your variable, and you're treating cosine v like a constant, right? V is a constant. So if that's a constant, what's the derivative of u? It's just 1, and then you just get cosine v, right? What's the next thing I need? Partial of y with respect to v. Okay, what's the partial of that with respect to v? Well, u is a constant, right? And then derivative of sine of v would be cosine v. So we just have u cosine v. Any questions? Okay, partial of x with respect to v next. Partial of this with respect to v. So this time u is a constant, and we're taking derivative of cosine of v, which is negative sine v. So I'm going to put negative u sine v. And then finally, partial of y with respect to u. Partial y with respect to u, which would just be what? Sine v. Okay? Now, let's plug it into this. Let's do the Jacobian. So for the Jacobian determinant, I'm going to call it capital J so you know what I'm talking about. Jacobian determinant, it's the magnitude, right, or the absolute value of that computation. So let's plug that in. Partial of x with respect to u was cosine v times partial y with respect to v was u cosine v. And then subtract from that partial of x with respect to v, which was negative sine v. I'm going to run out of room, so I'm going to move that. And then times partial y with respect to u, which was sine v. And that just becomes u cosine squared v, just multiplying those two cosines together. And then I have a minus minus, which is a plus. And then I have a u here, and then I have a sine squared v. And what you can do now is you can factor out a u from both of those, right? And you've got your Pythagorean identity there, don't you? So that turns into a 1. And so all you get is magnitude of u. But what was u for us? So it's r, right? And remember, r is that distance, the radius that you walk out, so it's going to be positive. So that's where the r comes from, right? That's where the r comes from. Questions? See, this works for any conversion. Polar is one conversion. You can go Cartesian to polar. But there's no restriction on conversions. All right? Did y'all hear what I said? There's no restrictions on conversions. You can convert any variable over to any other new system with any conversion you want. Whether or not it's beneficial or helpful is a different story. So this, you see this right here? If I wanted to, I could have called this x, I don't know, u squared plus v squared. I could have. And that would take it to a new coordinate system. Now that coordinate system is probably not very useful, all right? But I could do it. If I did it, I would need to compute this Jacobian determinant in order to scale everything properly, all right? That's called a change of variables. You're changing your variable from x, y to something new. Yes?
Are there any other like two-dimensional coordinate systems that we actually use?
I'm going to show you where this is valuable with some examples. Right now I'm just proving why with polar we get a r at the end. And then I'm going to prove why we get with spherical rho squared sine phi. And then we will do some examples where you can see where this would actually be useful to convert to a new coordinate system that's not polar or spherical or cylindrical. Just some new system we make up. All right? All right, good? All right, I need a couple of other things before I get to the rest. They call this the Jacobian determinant, right? Jacobian determinant. Here's why they call it the Jacobian determinant. Let me go back to what is a determinant for a matrix, right? So if you were given a matrices, right, something like this, A, B, C, D, right, and I ask you for the determinant of this, we've done this, right? When we were doing cross products, we had to do determinants. So what is the determinant of this? So the determinant, let's call this matrix A. The determinant of that matrix would be what, this times this, A times D, right, minus these two multiplied, C times B or B times C. That's the determinant. We're all okay with that? Okay, so if I now tell you to take the determinant of this, the partial of x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v. Now let's talk about this matrix that I created first. What I'm doing is I'm taking my x, right, my change of variable, and I'm doing the two partials for that variable x. First the partial with respect to u, then the partial with respect to v. Then I'm taking the second variable y, and I'm doing the two partials there. And then I'm taking the determinant. So what's the determinant of this? This times this minus this times this. And that's that. Okay? That is the determinant. So this is the determinant of this matrix. This matrix is called the Jacobian. That's called the Jacobian determinant, but they use the same word for both, but they're different things. You can read about it in the book. It talks about it. It's called the Jacobian and the Jacobian determinant at the same time. It's bad language, but this is the Jacobian, all right, which is basically a matrix made up of partial derivatives, and then when you take the determinant of that, you get the Jacobian determinant, which is the thing that you need in your integral when you change variables. Yes?
Is there significance to the Jacobian besides getting that determinant?
Is there a significant? Oh yeah, the Jacobian has a lot of different meanings to it. For us, let's stay in this though. Yeah. Yes?
Is doing like the reversion x, y, z simple as making a 3x3 matrix?
Yeah, so that's what I'm talking about now. So I'm ready to start going into spherical, right? And getting us to the point where we say, okay, spherical, we get this rho squared sine phi, right? But using this same logic, when I do 3 variables, right? When I do 3, let's think about what I would have. I want to see if you can abstract this idea. So if we go to 3 variables, right? And I want to make a conversion, my x is now going to be a function of how many things? 3. So I'm going to say u, v, and w, right? And then my y is going to be a function of what? 3 things, u, v, and w, right? I don't know what these functions are, but I'm changing my variable from x, y, z over to u, v, w. Z is some function of u, v, and w, right? So if those are my conversions, right, over to this new coordinate system, I now need the Jacobian and then its determinant. So let's make the Jacobian first. The Jacobian is going to be, first variable, you take all of its partials. Partial x with respect to u, partial x with respect to v, partial x with respect to w. Understand? The 3 partials across the top. The next row, you do the same thing for y. Partial y with respect to u, partial y with respect to v, partial y with respect to w. And then the last one is partial z with respect to u, partial z with respect to v, and then partial z with respect to w. So now I've set up my Jacobian. If I had 4 variables, right, and those were each functions of 4 variables, then I would set up a Jacobian that would be 4 by 4, right? 5 variables, 5 by 5, 6 by 6, 7 by 7. This extends out into whatever dimension you want to go to, all right? But I need the determinant of that now, right? So I need to hit the pause button here because I'm not quite sure how many of you are comfortable with the determinant of a 3 by 3 matrix. Most people know the determinant of a 2 by 2, but how about a 3 by 3? So just show of hands. How many of y'all know determinant of 3 by 3? Just curious. About half of you or so? Okay. So I'm pausing here. I'm about to talk about the determinant of a 3 by 3. So if I give you a 3 by 3 matrix, and I'm going to go real cheesy here. I'm going to just use A, B, C, D, E, F, G, H, I. All right? Let's say I have a matrix A, B, C, D, E, F, G, H, I. And I want the determinant of this. What you do, if I take the determinant of that matrix, what you do is this. Who can tell me? Somebody. You want to share? Go ahead. How did you learn it?
So I learned it by taking you take the minor of like the top left. And
You start with the top left,
Yeah, you start at the top left, multiply it by the minor of that top left.
Okay, so you start with the top left, right here, A, you put that here. Then you multiply that
By the determinant.
times the determinant of, you call it the minor, good, it's the, so once you pick A, you're wiping out this column and this row. You just ignore them. And you see those numbers remaining? Or those letters, right? You need the determinant of that. So that would be determinant of E, F, H, I. Okay, good, that's the beginning. Now what?
And then you have to alternate the sign.
Now you alternate the sign. So this was positive A times the determinant of what remained. Now you switch the sign and go minus. Now you move on to the B. And when you do the B this time, it wipes out this column and this row. So those are gone. And now you're going to do the determinant of what those four are left. So it's going to be B times the determinant of what, D, F, G, I, right? The D, the F, the G, the I, and then one more. And this one will be a plus. This one will be a plus. And then you do the C, right? And when you do the C, you're going to cover that up, and now you do the determinant of that. So times the determinant of DE, GH. And that's it, you're done. You go across the top row and you're done. Okay? Each one of these, right, what is this? This right here is what? EI minus HF. So I'll just do this first one. This first one would be A times, now in parentheses, E times I minus H times F. And I have to do that the rest of the way down. And for those of you who have not seen this before, or maybe this is the first time, what if you had this? A, B, C, D, E, F, G, H, I, J, K, L. What if you had a 4x4 matrix and you wanted the determinant? It's the same principle, right? So it's what? Well, oh, I'm missing one. Oops. I said 4x4. L, M, N, O, P. Sorry. There we go. 4x4. Right? So if we want the determinant of this, you start right here, right? So you start with A, and then times the determinant of what? FGH, JKL, NOP, which is a 3x3, which requires its own formula to do. Right? Yeah, have y'all seen? No? Stop. You get the idea, though, that like to do a 4x4 determinant, you actually need to do 4 3x3 determinants. Right? You're going to have to do 4 of them. And if you had a 5x5, you would have to do 5 4x4 determinants. And each of those would require 4 3x3s. And each of those 3x3s would require 2. Yeah, so it starts. So there is a general formula. You can look it up. There's a general formula for a general matrix. And it's a bunch of summations. And it's complicated looking because it's a little complicated, right? It's like these nested things that are happening within other things. So it's kind of cool. But all right, so we are only going to need this one right here. Okay? We're going to need this one. Let's go back to where we were. Because we're stopping there. Yeah, we're not going to go further than 3x3. All right, I'm ready. I'm ready to do, I think you have the framework in your mind, hopefully. Let's prove that when you do spherical, let's prove where the rho squared sine phi comes from. All right? You ready? This is going to be a grind. So let's start with the conversions. I'm probably going to wind up taking up a lot of board space here. I don't think it's practical for me to try and put it all in here. All right? So with that said, I'm going to put my conversions over here first. What are the conversions? Rho for x. Rho, cosine, theta, sine, phi. Okay, and then what's the conversion for y? Rho, sine theta, sine phi. And the conversion for z is rho cosine phi. Now, because I want to generalize this, I'm not going to use rho, theta, and phi. I'm going to use u, v, and w. That's just my choice, okay? I don't have to do this. The book actually does this proof with those variables, but I'm going to switch it. So x is equal to u, I'm going to use u for rho, cosine, I'm going to use v for theta, and for phi, I'm going to use w. So u sine v sine w, and then z is u cosine w. So all I did there is replace all my rhos with u, all my thetas with v, and all my phis with w. So this is where I was saying, and I hope this is clear to you, this is where we're saying x is a function of 3 variables, right? X is some function of 3 new variables. This is where I'm saying y is some function of 3 variables. And then this one is the z is some function of 3 variables. Now I hit pause a while back, right? I'm ready to unpause. Go back in your notes where I had paused, and here's where we were. We wanted to find the determinant of the partial of x with respect to u, partial x with respect to v, partial x with respect to w, partial y with respect to u, partial y with respect to v, partial y with respect to w, partial z with respect to u, partial z with respect to v, partial z with respect to w, right? I want the determinant of that. And that's where we have to start with the top left corner, right? Multiply that times the determinant of this, right? And do all that mess. So to be sure that I don't make a mistake, because there's going to be a lot of room for mistakes here, what I'd like to do is on the side, I'd like to go ahead and take all the partial derivatives now. And then I'll just plug them in later, all right? So let me take all my partials over here. Let's go around the room. Y'all can help. We can play together today. So partial x with respect to u. Okay, who's first? Go ahead. Partial x with respect to u.
Oh, this is scary. Cosine v sine w.
Cosine v sine w. Any objections?
Can I pick someone else now?
You pick the next one. That's a good one. I like that. Okay, Greg's up. You get partial x with respect to v. So I'm going to move my way across the top here. Okay, do all the x's first, then we'll do all the y's. Okay, what do you got? Partial x with respect to v. Let me erase this. So we're not even looking at that anymore.
Negative u sine v.
Negative u sine v what?
Sine w.
Sine w. Any objections? No? Who agrees? Only 2 people agree. Okay, thank you. So do y'all know that, have you ever heard of Fermat's last theorem? A little bit. It was proved recently. It was a famous theorem. It was unproven for many, many years. And it was proven. Huh? Well, no, it was his last theorem. It was kind of a joke almost. He wrote it in the margin of a book. And he is like, yeah, this can be shown. It's pretty easy, but I don't have enough space here to put the proof. That's what he said. And then, so it was kind of a joke. It was his theorem, but there was no proof for it. And then recently, within the last, 20 years or so, it was proven. And when it was proven, there was only like 1 or 2 people in the world that could even read the proof and make sense out of it. So it took years for the theorem to actually be validated, because mathematicians had to get up to speed with the way that this mathematician was thinking. And so the point of my statement here is that if everyone agrees, then it's true, right? I guess? I don't know. There have been theorems in math that are theorems that have proofs to them where people have found errors in the proof, which means the people who validated the proof missed something. It's kind of, I had a Russian professor for Cal 2, And he actually left and went to another college because he had found an error in a proof, and he got a lot of recognition for it because no one had seen that error before. Okay, so I'm going to continue. Partial x with is that good? Are we happy with this or no? Everyone's happy. Okay, you get to pick who's next. All right, we're just going to go across the table. Partial x with respect to w.
U cosine V cosine W.
U cosine v cosine w. Are we agreeing or not?
Yeah.
Yes? Yes. You have a question? Oh, you're saying yeah. Okay, who are you picking next? All right. Who wants the next one? You want the next one? Partial, we're doing partial y with respect to x.
Sine V, sine W.
Sorry, partial x. Partial u, sorry. Partial y with respect to u. Say again.
Sine V, sine W.
Sine v, sine w. Yay?
Yay.
All right. Partial y with respect to v is next. Are you picking someone or, oh, you're going? Okay. U cosine v sine w. We're all happy? One more, and we're done with the y's. Partial y with respect to w. Who's up? Go ahead.
U sine V cosine W.
U sine v cosine w. All right. Three more. Partial, where are we? Z with respect to u? Who's happening here? Who'd you pick? Z with respect to u. You're not up though. Right? You're up. So you get the next one now. So hold on, it's just cosine w?
Yeah.
Okay, cosine w, and now you get to do z with respect to v. 0. Good. This doesn't have a v, which means all that's a constant, and derivative constant 0. That's the first one that's kind of like, I don't know. I'm happy to see that actually. Partial z with respect to w is our last one. Go ahead.
U negative sine W.
U negative sine w. Can I put the negative in front? Negative u sine w. All right, now, if any of this is wrong, we are not going to get rho squared sine phi at the end, okay? If any of that's wrong. Now, I still have a lot of room to make mistakes because now I need a determinant, right?
Told us if we were wrong, or do you want?
I'm not even looking. I want to see if you're right or not. Okay, now, I'm going to write this out now. I'm going to write out the determinant of this without plugging anything in yet. So I'm just going to use the formula for determinant. So the determinant of this, which is the Jacobian determinant, is equal to, we start at the top left, that's partial x with respect to u. Then we multiply that